Hi guys, welcome to my thesis presentation. And it's based on an ongoing project in our research group. And the topic is navigating the task manifold. So the reason advances of deep learning generally consider different but related tasks together. The essence is just to leverage the shared information. Right? So we can utilize the model pre-trained on existing task to a new task. So such as multitask learning, continual learning, or transfer learning, right? So despite many useful applications and novel algorithms, less attention is paid to the fundamental questions, such as the causes of the task relatedness. And recent study points to a few directions, such as similar domains, similar features or learn representations, or even similar class distributions from the task-specific layers. But even less attention is paid to what happens to representations as well as the predictions when we switch a task, right? When we switch from an existing task to a new task, how does such switch impact the representations and predictions and how they update? So this is a main problem our research wants to answer. And before our project, there is already a few previous work to study the relatedness of the tasks, but all the tasks are pre-trained separately and embedded separately to the low dimensional space. As you can see in the plot, the plot A kind of effectively show the relatedness of the tasks. This is a task and the subsets from the ImageNet, and as we can see, it coincides with a tree, which is word meanings, right? So as we can see, the main branch is ImageNet, and then it subtract to smaller classes such as animal and artifacts and so on. So from the plots, we can observe that actually similar tasks will work more closely throughout the training, while different tasks will diverge. And the plotting B is just a quantitative metric to measure the distance based on the convergence. And we can see some different tasks actually will diverge throughout training. So we were wondering, what if we put this setting in a multitask learning, right? What if we learn all the tasks jointly? Will they still behave the same way and have the similar trajectories? And based on that, we want to investigate what is a transfer learning trajectory, right? So whether we can use the previous task trajectories and project to the new task as a transfer learning. So in general, our study considers k in-domain classification tasks, where each task is represented by a dataset, right, with n sub k samples, and each task can have different number of categories, c sub k, but we can use summation to get a total number of samples and the total number of categories, and hence we can define the n by c prediction space as a function output, where the function output is just a prediction based on the model outputs. So in total, we can have a k by t by n by c trajectories forming a space, right? And where each point is an n by c output and specifically the model at a time step t. So before we all start, we want to draw some theoretical motivations from. Actually, this part is based on the Amari's book, the information geometry and its applications. So we generally refer and follow to, and essentially we want to verify that there can exist a kind of flat manifold that's easy enough for us to derive some simple geodesics. So it's like more easy to optimize and learn. So for example, when we measure the distance between two cities, we want to measure the distance from the sky instead of on the ground, counting the mountains and valleys, right? So in order, so we generally show that we can have a dualistic structure, and which its third order derivative is will vanish, and thus we can show it's somehow flat. So to begin with, it defines two coordinates. The first one is m coordinates, which is just the class probabilities if we take the first class as a reference. And the second one is the e coordinates, which is just a softmax version of the m coordinates. But we can use the e coordinates as a gradient of the bottom convex function. And based on the convex function, we can define the Bregman divergence as shown in the first equation on the left. But at this point, we do not observe any flatness because the derivative does not vanish. However, we can introduce a dual function. Sorry. However, we can introduce a dual function of phi taking p, which is a p log p of the m coordinates over the summation of like m and I, right? So combining the dual function into the Bregman divergence, we can have a dualistic version of the Bregman divergence. And at this point, we can observe that the third order derivative of the divergence, which is a fine connection between theta and the p, equal to 0, right? With respect to d theta squared dp equal to 0. That means a fine connection will vanish. So it's possible that there exists a flat manifold and simple divergence geodesics, and we want to build our task manifold in the same way, so that we can kind of learn the basis of the task, and on the right is kind of a generalized form of our hypothesis, right? We can define the task manifold M, which is d-dimensional and represented as a weighted basis, where the basis is based on the previous task we pre-trained. And the generalized objective is just to minimize the Bregman divergence between the generated output with the ground truth, right, over t time steps and the k tasks. So before we try to implement them practically, we want to have some value measures on the Bregman divergence. So the following plots are based on a single task pre-training on Cypher 10, and we use intensive PCA to embed them into low dimensions. And as we can see, with the increasing number of training steps, the Bregman divergence actually stabilizes. And what's more is that while the dimension is larger than 5 or 10, it actually does not change much, right? So that means the such divergence, and it's possible for us to like effectively embed them into a low dimensions, and maybe the task manifold is just low dimensional. So this figure is just another two quantities for us to further verify our ideas. The first one is the numerator is Bregman divergence between theta t and theta t hat. So theta t hat is just a projection of theta t to the low dimensional space, because we are embedding theta t to the low dimensions, and we assume that we cannot fully capture we cannot fully capture theta t to the low dimension, but we can, as we can see in the violin plot, with the increasing number of dimensions, actually the numerator is approaching 0 effectively with more and more centralized distributions. That means despite we need to increase the number of dimensions, we can effectively embed everything into kind of low dimensions, for example 50, right? So, and the subplot on the right is just another quantity to prove the same idea, and which is a divergence between the initial point to the projection, and from projection to the theta t subtracted by the direct divergence. So yeah, it's a good signal for us. That means we can use some limited number of dimensions to embed them into a subspace or specifically our task manifold. And then we try to just implement it, right? The first step is to gather all the tasks we need. So we just propose a simple way to explore the task space, which is just random search. So at the beginning of the training, we'll just sample a task from all the tasks according to a uniform distribution. And for each time step, there is a very small probability to switch the task based on the P switch. So then we perform the training and update the model parameters. and in the end, we will save and record the EMA version of the model, which is just a exponential moving average. And as you can see, it's kind of basically a decay function within the stop gradient. So after we gather all the tasks, they still have different number of categories, right? So in order to utilize them jointly, we derive a task imprinting method, such that we can imprint the task from one task to another, right? So for example, we want to imprint the task from task I to the task J. Since they share the same backbones, we just have to imprint classifiers in a similar fashion of cosine similarity as shown in the bottom left, where the capital 1 is just an indicator function. And moreover, we can use the task imprinting to imprint all the tasks to a common space, where the capital C, right? So that we can evaluate them in the n by c dimensions. And since we gather all the task trajectories, we can embed them into a low dimension together. So we have given the eigen decomposition of a W matrix in the PCA. It's equal to half of the LDL, where L is just a centering matrix and D is a divergence matrix. Previously, we used Bregman divergence for theoretical motivations, but one can check that it actually coincides with KO divergence and equivalent. So we can just use a Bhattacharya distance right here. And after we gather everything we want, we can just compute the low dimensional matrix X for each task, and it's of some arbitrary dimensions R by R. And so this is a intensive PCA visualization of the first 3 dimensions of all the tasks. And the left plot is a multitask pre-trained learning on Cypher 100, where the tasks are divided based on the superclasses. So we have 25-way classification tasks. And as we can see, actually, we randomly pick 4 tasks for clear visualization, and we can observe that they are similar, right? They have a similar stars in the center, and have a similar like triangular or tree shape. And from the plot, we can observe that actually red task is more different from the rest, while with later training, the orange and the green task kind of become closer. And the subplot on the right is just a multitask pre-training on Cypher 10, where we sampled we randomly sample 20 tasks. So for this setting, the C sub k, right, the number of categories for each task is different. And as we can tell, it's more there are less patterns and it's more messy than the left subplot, but we can still observe kind of like general shape. And we can have they have some clusterings in the middle, and the blue and the red tasks are kind of more similar, while orange and the green are kind of similar. So based on this, we kind of empirically show that well, maybe the task manifold is no dimensional enough. So we can just derive a basis for all the tasks. So we go ahead and derive the basis matrix for each task, where we can just, where the derivative of the low dimensional embedding is just matrix multiplications, as shown here, right? So we can pick m dimensionals to embed them into a m dimensional space. And since we record since our like time steps are discrete, for example, we save the checkpoints each iteration, right? So we need a kind of more continuous time embedding. So we introduce a learnable time embedding as shown in the expression, and combining them together, we can have a transition function to transit the low dimensional embedding x t time steps forward, right? So we can project them a few steps forward to form a trajectory. And based on the transition function, we can just compute the loss as a norm square between the transition embedding and the ground truth embedding. And this is a loss function for a single task, right? And we can have a generalized form of the objective to minimize such loss over t time steps and the k tasks. And yeah, yeah, as you can tell, this project is still ongoing, and there are still a few issues to investigate, but we have some very initial results, and despite the results are not really satisfactory, we can still observe some overlaps between the ground truth and the prediction trajectories. So they are all like they are all low dimensional embeddings. And based on our previous investigations, we also derive some ideal way to perform transfer learning. The first step is just to imprint all the previous models to the new prediction space and embed them into the proposed low dimensional embeddings. And the next step is basically to find the best task from all the previous tasks as a starting point for our transfer learning. So yeah, given all the basis matrices and the intensive PCA embeddings, we can find the optimal task as follows, and we fine tune from the optimized task to the target. But ideally, the best way we think is just to construct a brand new task from the same domain as a projection task, which is a theta t hat we previously see, right? And we perform transfer learning from theta t hat to theta t, right? So yeah, there are a few limitations which also point out to future work. The first one is we need to generalize it to more multitask settings, such as different tasks. So yeah, for example, given a scene of this classroom, we can have like segmentation, we can have depth estimation and edge detections, right? So all the tasks in the same domain, as well as cross-domain problems where we have different like input sources. And the other direction is just more theoretical analysis, because since we have all the task trajectories in the low dimensional task manifold, we can actually derive some generalization bound just based on the volume of the manifold, right? So yeah, I think that's also a promising direction. And yeah, basically that's all for my presentation, and thanks for listening. And I also want to thank my professor Chaudhari and Yansong Gao, my senior PhD, for their help. So the question is how we use the basis function to inform the capabilities of. Okay, so how to inform the capabilities of robots needs to have in order to complete the task. I see. So I'm not a robot guy, but but right. So so we have the basis for each task, right? So each task in a, I think in a robotics setting, each task can correspond to some each robotics task, right? What are they like? That yes. Sure. Sure. The two questions are ask us whether we can generalize it to more broad settings, right? So as I mentioned, each task can have different number of categories, which is C sub k. So at this point, we can just for different tasks. So for if we have two tasks, right, and they have very different like outputs, right? For instance, the first one is just a classification, and the second one is segmentation, where the C sub k is just should be the mask, right? So we can just flatten it, right? So and then concatenate it. So for instance, if a first task has how to put this? So if a first task has only one channel output, while the second task has like 1,000 channel output, we can just concatenate it, right? So it should be just 1,001, right? So and we can also like reflect to a general common output layers, like with 1,000 plus 1 channels.